Today we have an honor to have Professor Dimca in us, who is going to present on the Tjurina numbers of projective plane curves. Professor Dimca is one of the renowned persons in the area of algebraic geometry, and one of the reason is behind his contribution in the area is the three major books he has written, and which is considered as the textbook in the area of research of algebraic geometry. I don't think you can find any paper using the sheaf theory and major techniques which has been discussed and evolved through the work of Professor Dimca, and which is mentioned in his books. And the title of his three books are Hyperplane Arrangements, one of the foundational work of Professor Alexandru Dimca, and it contains many important aspects of hyperplane arrangement. Then sheaves in topology, and the third book is Singularities and Topology of Hyperplanes. So over to you, Professor Dimca, and today he's going to discuss about on the Tjurina number of projective plane curve. Welcome to John Conway Separated Seminars.
Yes, thank you very much for the invitation. So I will discuss a topic on which I worked in the last few years, and where there are a number of open questions. And I will describe these open questions for you. And if some of you have idea how to solve them, so much the better. So I will be happy to see solutions to these questions coming from you. Okay, now it's a little problem because I cannot move it. Okay. So this is what I plan to discuss. So you see, first I will discuss the local Tjurina number, and then I will present the main characters of our story, and then I will describe the results and finally reference for some of these results. So to define the local Tjurina number, we start with a ring of convergent power series in two variables, u and v, with complex coefficients. And for any power series S in this ring, we define its Jacobian ideal, GS, to be the ideal in R generated by the partial derivatives with respect to u and v. And then the local minor algebra is just a quotient, MS, of this ring of power series by this ideal, Jacobian ideal. And if this algebra is finite dimensional as a C vector space, then we say that S has an isolated singularity at the origin and define the minor number to be the dimension of this quotient. And then we define another algebra, which is Tjurina algebra of S. And to do this, we increase the Jacobian ideal by adding a new generator, namely the equation S. The series S is added to this ideal. So we get a bigger ideal. And so the quotient will be something smaller. And if this algebra is finite dimensional, then we define the Tjurina number to be the dimension of this new algebra.
Excuse me, Professor, what do you mean by the ring of convergent power series? So this is different from formal power series ring?
So you can work for this definition, you can work with formal power series. If you are really people working in algebra, you prefer maybe formal power series. In this case, all the definitions are the same. But convergent power series is what people use in complex analysis. An analytic function or a holomorphic function is the same as a convergent power series.
Okay, thank you.
So if you have an analytic function in two variables, at the origin, it has a Taylor series, which is a convergent power series, okay? But it's not important, this difference here is not important. Okay, so in general, Tjurina number is smaller than the Milnor number, and the equality holds if and only if our series is weighted homogeneous, which means that by a local analytic change of coordinates at the origin, our series become a weighted homogeneous polynomial. And you will see examples in a moment. For instance, if S is a homogeneous polynomial, for instance, given by U power k plus V power k, then the Milnor number coincides with the Tjurina number. This is just k minus 1 squared. And if you want to look at the zero set of S in the complex plane, this is just a union of k lines passing through the origin in the complex plane. And another example to see what means weighted homogeneous polynomial, you have this U2 plus V power k plus 1. And then the Milnor number is again the same as the Tjurina number, and this is k. This is a so-called AK singularity in Arnold classification list. And finally, an example where the two numbers are different. This is this series, which is actually a polynomial. So you see, can be regarded as a formal power series if you like. And here the Milnor number is 11 and the Tjurina number is 10. And how can I compute these numbers? Well, I guess you are familiar with the software Singular, and in this software, there are simple commands to compute Milnor and Tjurina numbers in any number of variables. That is, instead of looking at power series in 2 variables, you can work with power series in 3 or 4 or more variables and compute Milnor and Tjurina numbers. Okay. So, any questions about this part? Okay, then we really start our story now. Now we move from power series to polynomials. So in some sense, a simpler object, but we increase the number of variables. So now we have 3 variables, x, y, z, and f is a homogeneous polynomial of degree d. And C is a 0 set. And so this is a plane curve in the complex projective plane, P2. And I assume that it is reduced. This means that the polynomial f has no multiple factors. So it can be a product of factors, but all the factors are distinct. And as a special case, I consider the case of line arrangements. And in this case, f is a product of linear forms. Because in this case, if I look at the 0 set, I get lines, because the equation of a line is a linear form. And then I consider the Jacobian ideal, GF, in the polynomial ring S. So S is a polynomial ring in 3 variables. I consider the saturation of the Jacobian ideal, which is defined by this operation, so division of 2 ideals. M is a maximal ideal, and I consider the quotient of these 2 ideals, which is denoted by an F. And you know that the polynomial ring is a graded polynomial ring, it's graded, and so the Jacobian ideal is also graded because f is homogeneous. And so this quotient will also be a graded S module. And this graded S module was introduced by an Italian mathematician, Cernesi, and he called this Jacobian module of f or of the plane curve C. And now we define the global Tjurina number, tau of C, to be the sum of all the local Tjurina numbers. So I look at all the singular points of the curve C, I make the computation, which I explained to you in the beginning, and I get a number. And then I make the sum of all these numbers. And this is a global Tjurina number of the curve. If you are more on the algebraic geometry or commutative algebra, this global Tjurina number is exactly the degree of the Jacobian ideal. So any homogeneous ideal has a degree, which is the degree of the associated scheme in P2, and the degree of the Jacobian ideal is just the global Tjurina number. So there are two ways of looking at this global Tjurina numbers. And then I can look at the partial derivative, fx, fy, and fz, and I can look at all the linear combinations equal to 0, but instead of putting here complex numbers, I will use homogeneous polynomials of degree k. And I will denote this vector space with this notation. And when I make the sum of all these graded spaces, I get a graded S module, which is a module of all Jacobian relations of f. And this tells me how independent are these partial derivatives. And if you know what is the coherent sheaf associated to a graded S module, then we can consider this sheafification, and this will be a rank 2 vector bundle on P2. And this is related to the sheaf of logarithmic vector fields along C. But even if this is beyond your knowledge, don't worry, this will appear very little in the sequel. So the main object will be this object, and you see that this object is quite elementary. If you know how to compute the partial derivatives, just to look at all relations of this type. And what is very important is a minimal degree of such a relation. So I look at the minimal degree, which is non-trivial, that is at least one of A, B, and C is non-zero. And this is called the minimal degree of a Jacobian relation. And this is always smaller than D minus 1 because I can always obtain a D minus 1 relation in the following way. I multiply f of x by fy, and then I take A equal to f of y and B equal to minus f of x. And so I obtain some very simple relations of degree D minus 1. But usually there are a lot more interesting relations among these partial derivatives. And a curve C is called free if this module is a free module, as a free module of a polynomial ring. And one knows that this is equivalent to the quotient n of f. So this Jacobian module equal to 0, that is the Jacobian ideal is saturated, or that this vector bundle splits as a direct sum of two line bundles. And these numbers which appear here will be called the exponents of the free arrangement.
Here D means the degree of the polynomial f?
Yes, D is a degree of the polynomial f. And here is D minus 1. And if this splits, then here we get two new integers, D1 and D2.
Okay.
And now, what is the first important open question on which you can work if you like? So Terao conjecture was made 40 years ago. And it concerns hyperplane arrangements in arbitrary dimensions. So his conjecture is more complicated, but we will look now only at line arrangements. And even in this case of line arrangement, so in projective plane in P2, even for line arrangements, this is not yet known. The answer is not yet known. And the question is like that. Suppose we have two line arrangements which have the same combinatorics. This means that suppose they are real line arrangements. So suppose you can draw the pictures, the two pictures looks the same. So there is no difference in the picture. Maybe if you look at the equations, the coefficients are different, but the picture looks the same. And assume that one of them is free, one of the two line arrangement is free. Does this imply that the second one is also free? And there are a lot of work. In many cases, it is known. For instance, if the number of lines, which is a degree, is up to 14, the answer is yes. So this implication is true. But in general, we have no idea. And one may think that all the invariants we have defined until now are determined by the combinatorics, but this is not so because a famous German mathematician, Ziegler, in 1989, he discovered two line arrangements with the same combinatorics. Both of them have degree 9, and minimal degree for one is 5 and for the other is 6. And moreover, these line arrangements are not very complicated because they have only double points and triple points. That is, points where only 2 lines meet or points where only 3 lines meet. And this is a number of double points and number of triple points. And so even for such example, not very complicated, these two numbers can be different. And you will see that there is a relation between freeness and these numbers, this minimal degree of a relation. You will see this right now. So now I will discuss a theorem due to mathematicians in 1999. So for two integers, R and D, satisfying this relation, we define two new integers, minimal Tjurina number, depending on D and R, and the maximal Tjurina number, depending on D and R. And why are we introducing these two integers? Because we have this result for any reduced plane curve of degree D, with R being the minimal degree of a Jacobian relation. The Tjurina number which we defined before, that sum of local Tjurina numbers, is between these two values, minimal and maximal Tjurina number. So this is very interesting result, but so without knowing anything concerning the singularities, we know that this inequality holds. Moreover, if this minimal degree of a relation is bigger than D over 2, roughly, then we have a stronger inequality. That is, we can decrease this maximal Tjurina number by some binomial coefficient. And so this is defined by tau max prime. And in addition, on the other, if we have the other inequality here, so if R is smaller than half of D minus 1, then we can characterize the free curves. A free curve is, a curve is free if and only if the Tjurina number is maximal. And this is a beautiful result because it's enough to compute Tjurina numbers and check this. So we have to know the degree, we have to know the degree, we have to know R, we have to know D and R, and then we compute the Tjurina number, and if we have this equality, then we can decide if the curve is free or not. Okay, so Duplessis' Wall theorem has a version in higher dimension. So so there are questions?
Yes, please. If I may, what do you mean? I mean, is there an easy way to interpret this geometrically? What do you mean by a curve being free?
So there is no geometric picture for this. I gave a definition of a S module. S is a polynomial ring. We have a module, and the curve is free if this module is a free module. So do you know what means a free module? It's like a vector space.
Yeah, I know what a free module is, right?
Okay.
So there is no easy geometric
so
picture.
The only geometric description is that I define a vector bundle, and the geometric description is that that vector bundle is a direct sum of two line bundles. This is the only geometric description.
Okay, right.
It's not intuitive.
Thank you.
If you are not used with vector bundle, it's not intuitive, but this is the only description. And that's why this result is important, because we have a simpler way to check.
Right, thank you.
Okay. Now, the Plessis-Wall theorem has a version in higher dimension. So you see, essentially, this applies to hypersurfaces of degree D in Pn. But now I have to add that they have only isolated singularities, because Tjurina numbers are defined only for isolated singularities. And we define the minimal degree relation exactly as in the case n equal 2. That is, we look at all the partial derivatives and we look for linear relations involving them. And then we have this inequality. And you see, we just multiply the previous values by d minus 1 power n minus 2. And moreover, these bounds are sharp when R satisfies this inequality. And there are two comments here. First of all, that if I look in higher dimension to hypersurfaces having isolated singularities, such hypersurfaces are never free. And so we cannot, the problem is not about deciding which such hypersurfaces are free, but the problem is the following. You have seen that when R is bigger than d minus 1, for n equal 2, we had a better upper bound, which was denoted like that. And if I multiply this bound by this factor, I may try to prove this inequality. But this inequality is not true, so there are counterexamples to this. And so the first open problem for you, for instance, is can you find some upper bound here, which is better than this? Because this, which was suggested by the case n equal 2, is not true. So this is not correct. This is not sharp. And so can you find something better than this, which holds for any n? So this is one open problem for you, if you like. Okay, so now I will discuss some of my results with several co-authors you have seen. So for any curve, I can define a freeness defect in the following way. I look at the quotient n of f, and there are homogeneous components. So nfs, this means a homogeneous component of degree s. This is a vector space. I take the dimension and I take the maximal possible dimension of this. And one knows that this dimension is obtained for some special value of s. Here I forgot to say what is t. T is 3 times d minus 2. Sorry for this. This is anyway not very important. What is important is that this freeness defect is indeed tells me when a curve is free, because a curve is free if and only if this is 0. this follows from the fact that I say that a curve is free if and only if this module is 0. And then I define the notion of a nearly free curve when this invariant is 1. And we are interested in these curves from the following fact. There is a conjecture by myself and Gabriel Sticlaru, which says that if I have a projective plane curve, which is homeomorphic to P1, this means homeomorphic to a two-dimensional sphere, then this curve is either free or nearly free. And being homeomorphic to P1 can be replaced by the curve C is rational and cuspidal in the sense that all singularities have just one branch. And this conjecture, we were able to prove it for all even degrees and for most odd degrees, but not for all. So for instance, when D is more than 90, there are 9 pairs DR for which the conjecture is open. And so if you have an idea how to prove this conjecture for all odd D, this will be very interesting. And you can find our proof in the literature. I will give the references at the end. But maybe our proof is too complicated. Maybe you can find a simpler proof because everything here is very elementary. So you have seen the definition of free is quite elementary. Being rational means that it can be parameterized by some rational functions. And so there is a possibility that there is a simpler proof than the proof we have found, and a proof which works in all cases, but we don't know, of course. Okay, and then I have another result which describes the relation between Tjurina number, this maximal value of the Tjurina number, and this freeness defect. So you see freeness defect is just the difference between these two numbers. And this is, of course, a generalization of the fact that the curve is free if and only if we have equality here. And moreover, you see that when R is bigger than this value, then this invariant, this freeness defect, depends only on the Tjurina number. This minimal degree R is no longer present in the formula, and this is maybe interesting because now we come back to Terao conjecture, and I can reformulate it in the following way. So first of all, the Tjurina number for a line arrangement is determined by the combinatorics because it's determined by the number of double points, triple points, and so on. Because a k multiple point has a formula for Tjurina number exactly k minus 1 power 2, so square of k minus 1 power 2. And so when I make the sum, if I know how many multiple points for each multiplicity I have, I get a formula for the Tjurina number. And so the reformulation is like that. If I have two line arrangements with the same combinatorics, and if one of them is free, then this invariant should coincide. That is, counterexample like Ziegler counterexample cannot appear if I assume C is free. This is a reformulation, and in some sense, it's maybe more elementary because you see here the fact that it's free appears only here, and then we have to check some numerical equality. And I have also a generalization of Terao conjecture that is a statement which is much more general. So if we have two line arrangement having the same combinatorics, then these two numerical invariants coincide. And this is a generalization because free means that this invariant is 0. And the generalization means, tells me that the fact that it's free is not important. The combinatorics determines this invariant. Yes. So there are some questions.
Samir, do you have any question? Okay. Continue, Doctor. Sorry.
Okay, no problem. So because we have a more general conjecture, which is somehow more algebraic because this is really commutative algebra, maybe it's easier to construct counterexamples. So please try to construct counterexample to this conjecture. And this will be very much appreciated by an international mathematical community because in some cases, this holds. For instance, if I have a line arrangement which has a point of high multiplicity, this I can prove, then I can prove that the conjecture holds. And also it holds if it has only points of multiplicity up to 3, because in this case, we have this inequality. And this does not contradict Ziegler counterexample, because in Ziegler counterexample, these two invariants are distinct, but these two invariants, if I compute for his example, these invariants are the same. They are different from one, but the same. And so Ziegler counterexample is not a counterexample to this conjecture. So one good question for you is to try to find counterexample or a proof for this generalization of the Rawls conjecture. Okay, so until now we have considered free curves, and free curves you have seen have maximal Tjurina number, but they satisfy also this inequality. And it is easy to show that for any pair dr where R satisfies this inequality, there exist line arrangements and also irreducible curves, so any kind of possibility, which are free. So constructing free curves of given degree and given minimal degree, which satisfies this condition, is possible for all the pairs dr. Okay, so now I like to see what happens when R, when this invariant is bigger than D over 2. So I go to the opposite inequality. So I assume this. And now I know that the possible maximal value is no longer this tau max, but tau max prime, because you recall that we have a subtract binomial coefficient from this tau max to get this tau prime. And so this is the maximal possible values. And so now there are natural questions. Does there exist curves realizing this possible maximal value? And we made a conjecture. For any integer D and for any integer R satisfying these inequalities, there are maximal Tjurina curves of type dr. This means curves which have degree D and R is a minimal degree of the equation, such that this equality holds. And moreover, when R is smaller than D minus 2, so I get a little bit smaller than d minus 1, so I put here d minus 2, I can construct maximal Tjurina line arrangements of type dr. So this is a conjecture, and we know some facts about it. First of all, this conjecture tells me that Duplessis wall upper bound is sharp for any power dr. And this would be a beautiful result, because usually when you have inequality of this type, they are not sharp, but if this conjecture is true, this shows Duplessis theorem is the best. And moreover, as an example, a curve of type 2RR is exactly a nearly free curve with degree 2R and the minimal degree relation R. So one can look at maximal Tjurina curve as a generalization of some class of nearly free curves. Okay, so now we have many information about maximal Tjurina curves in terms of free resolutions of this S graded S module, and we have explicit construction in many cases. And here are two examples. First of all, in a joint paper with Japanese mathematician Takuro Abe, my friends from Romania, Gabriel Sticlaru, we show the following. If we have a pair of positive integer satisfying this inequality, then there is a real line arrangement in P2, which is Tjurina maximal and satisfy D is equal to the number of lines and R is minimal degree of a relation. And so being real, this means that all the equations of lines are real, and we can really draw the picture in P2 or even in the real plane. And so this is a way to find examples and counterexample. You just draw a real line arrangement in the plane, compute the invariants, and then see if it's an example or a counterexample to an open question. And to understand the second construction, recall that for any degree, there are irreducible rational nodal curves of degree D. And such a curve has exactly this number of nodes and no other singularities. And these curves are called maximal nodal curves by Mutsuo Oka. And we have the following result. A line arrangement satisfies always this inequality. And so that's why we cannot construct maximal Tjurina line arrangement with value D minus 1 here. But if we want to have maximal Tjurina curve with D minus 1, then it is enough to take a maximal nodal curve of degree D, as I explained before. So a curve of degree D with maximal number of nodes. And our results also imply that our conjecture on the existence of maximal Tjurina curves hold for all the degrees up to 11. So if you look for counterexample, you have to start with 12. Okay, so now you have seen that in Duplessis wall theorem, there are two parts. There are some upper bounds and some lower bounds. And so now I look at the lower bound. And I ask, what about minimal Tjurina curves? That is, minimal Tjurina curves which realize a minimal value. And the answer is yes, such minimal curves exist. So if I take a curve which is a Thom-Sebastiani plane curve, that is a curve which is obtained like that. I start with a homogeneous polynomial in two variables, g, and then I add just z power d. And this polynomial in two variables, because it's homogeneous, it always splits as a product of linear forms. And if they are distinct, then can be written in this form. And then it is easy to show that the minimal degree relation of such a function is m-1. So the number of factors here -1. And there are two other relations which have degree d-1, but this is not important. What is important is that if I compute the Tjurina number, and this is very easy here, I get this value. And so this means that all these curves are minimal Tjurina curves. And so any possibility dr can occur because I can take m, any value I like.
Professor Dimca, what do you mean by 3-CCG curve?
3-CCG curve, yes. You know, I look at that module AR of F, and this module is free if it is it is always a module of rank 2. And this means if it is free, it is generated by 2 elements, right?
Mm-hmm.
But if it's not free, then it can have a larger number of generators as an S module. So the rank is always 2. That is, if we tensor by the function field of the polynomial ring, then we get a vector space of dimension 2. But as a module over S, it can have a larger number of generators. And the 3-CCG curve, it's a curve where we have 3 generators for this module. And these are the degrees of the generators. But for our discussion, this is not important. What is important is that if I want to construct minimal Tjurina curves for any pair D of R, I can do this by this very simple construction. So this is the main point here. And so now I can ask, what about minimal Tjurina line arrangement? So these curves here are not at all line arrangement because we cannot split this as a product of linear forms. Okay, and so we prove that minimal Tjurina line arrangement do not exist. And so some notation, first of all, for a line arrangement, I said already that global Tjurina number can be computed from the combinatorics. You see, you just make the sum of all intersection points. And this is a multiplicity, how many lines meet at that point. And this is a formula for the global Tjurina number of a line arrangement. So Tjurina number is just purely combinatorial, and our question is again purely combinatorial. And I denote by M C the maximal multiplicity of a point in C. So I look at the point where a maximal number of lines come together. And NC is a maximal multiplicity point of C minus this point. So I look at the next point with highest multiplicity. And of course, I have this inequalities. And it is known that maximal multiplicity is D if and only if all the lines meet in one point, and this happens if and only if minimal degree of a relation is 0. And maximal multiplicity of a point is D minus 1 if and only if minimal degree of a relation is 1. And so it was known that there are some relations between these numbers. And so now we see what happens in general. Here is a theorem which says that if I assume this number to be at least 2, because this is a really interesting case, the other cases are listed, and I recall the formula for the minimal number, then the following holds. Our Tjurina number is always bigger than something minimal prime, and this prime means that I start with this minimal value and I add one binomial coefficient, another binomial coefficient, and plus one. So this number is strictly positive, and this means that for a line arrangement, one can never have Tjurina number equal to this minimal value. And if some additional condition holds, then maybe a stronger inequality holds, because I can replace this binomial coefficient by some larger, possibly larger value. And so this shows that the minimal Tjurina curves behave quite different from maximal Tjurina curves, because for maximal Tjurina curves, we believe they always exist. And for minimal line arrangement, we show that they never exist. So life is different if we look at minimal values and maximal values. Okay, so line arrangement with small minimal degree relations have been classified by Tohaneanu. He's a Romanian mathematician working in the United States. And so when these numbers are 0, 1, 2, and 3, we have a complete list of such line arrangements. And when NC is equal to 2, then this arrangement corresponds to an arrangement obtained from some number of concurrent lines by adding some line in general position. So everything is clear. There's just one possibility for such arrangement. And for the remaining line arrangement, we have this corollary of the previous theorem, that not only this cannot be equal to the minimal value, but the difference is at least equal to 7, you see. Okay, and so now what would be an interesting open problem here? We have seen that this minimal value is not a sharp lower bound in the case of line arrangement. So an interesting open question would be, can we find a better lower bound for the Tjurina number of line arrangements? A better lower bound means some expression which is better than what I have in my theorem here. I have already a better lower bound than what was given previously by this number. But can you find something even better than these two numbers, and which is still a lower bound for the Tjurina number? Because these inequalities are not sharp, I guess. In this case, sharp, and so it's quite likely that there are better lower bounds than these two formulas. Okay, and so at the end there are some references, and anyway, I guess you can find all this on archive. And this was all I wanted to tell you. Thank you very much. And now I'm waiting for your questions.
Oh, thank you, Professor Dimca, for a wonderful talk. Any questions from the audience? Please feel free to ask any question.
Of course.
If you have.
Don't be shy.
Yeah, Hania.
This may be a stupid question, but
there are no stupid questions.
No, then this could be a really stupid question. Is there a connection between? So you talked about. The curve being free and characterized in terms of the global Tjurina number.
Yes.
And I might have missed. Is there is there a connection between the freeness of a line arrangement, or is it something that's given that you know when you look at an arrangement, or is it something that you need to find out? And the global Tjurina number in this situation? Is there a connection?
If you have a line,
like one thing to the other?
Yes, so if you have a line arrangement, it's very easy to compute a global Tjurina number because you have this formula which is here. So this formula. So this you can compute, and this is determined by the combinatorics. And the problem with Terrao's conjecture is that in that conjecture, you have this to prove Terrao's conjecture, you need to show that two numbers are determined by the combinatorics for free curves. First one is Tjurina number, and this is no problem. But the second one is minimal degree of a relation. And this minimal degree of a relation is not, you cannot write a combinatorial formula for it because of Ziegler example in general. But maybe for free line arrangement, there is a formula. We don't know.
So that's a question then.
So that's a problem. How to relate, if you want to approach Terrao's conjecture using the viewpoint of this talk, then you have to control a minimal degree of a relation. And this is not clear how to do.
Right, thank you.
Yes, Shaheen.
Hello.
Hello.
Hello, how are you?
Fine, thank you.
Okay. I have a question about, is there any relation between these modules, Tjurina modules, and between the Orlik-Terao algebras, Orlik-Terao ideas, which makes Orlik-Terao algebra. So have you seen some relation between these two modules or something like that?
I don't know. So to tell you the truth, I don't know. So maybe it's a good question. I don't know if there is a relation. I never look at these algebras, and so maybe it's a good idea for you to try to see if there is a relation.
Okay. Okay. Thank you.
Okay, any other question from the audience? Okay, I think it's time to say goodbye to everyone. Thank you, Professor Alexandru Dimca, for accepting our invitation and for sharing your time and presenting these beautiful results with a lot of open problem. And we will put up the recording of this particular talk on the webpage, and feel free to contact Professor Alexandru Dimca if someone has any long question to discuss.
Yes, and I can send you the file of my talk also if you like.
So yeah, I will place it.
You can share it.
Yeah,
you can share it with people if they are interested. So, but I like to tell you from the beginning that all the open questions which I mentioned and the conjectures, I don't know the solutions. These are not exercises for you. So I don't know the solution. Of course, if you have idea, I can look at your ideas and tell you if this gives a solution or not, but I cannot guide you toward the solution. I hope you understand.
Yeah.
Okay.
Thank you, Professor Dimca. Thank you, everyone, for joining us. See you. Bye-bye.
Bye-bye. See you.
Bye-bye. Bye-bye, Alex.
Bye.
Bye-bye.
Greeting from Vietnam.
Yeah. How are you?
I'm fine. It's very interesting talk. Yeah.
Okay. So
I am happy to join your seminar.
That's nice. Yeah, that's nice too.
Yeah.
That's nice to see you.
Talk
With.
a little bit, yes.
Yeah.
So sorry, my computer have some so webcam on my computer was destroyed.
No problem.
So, yeah.
At least we can talk. At least we can talk. That's good. Okay.
Yeah.
Okay.
I hope everyone has good health in these difficult times, you and your families.
So Alex, sorry, I have just a very small question because I missed some point in your talk. So
Yes.
are you dealing with the Terao conjecture for any hyperplane arrangement or only for the line arrangement?
Only for line arrangement. This methods work only for line arrangement because Tjurina number is defined only for isolated singularities.
Okay.
And in higher dimension, free hypersurfaces have never isolated singularities. This is known.
Yeah, I see.
Yeah, so a free surface, for instance, or a free plane arrangement in P3 should have one-dimensional singularities.
Mm-hmm.
And so this is more complicated to control.
Okay, thank you.
Okay. Okay.
Thank you.
Best wishes for all of you.
Okay.
Thank you.
Yeah,
bye-bye.
Bye-bye, John.
Bye-bye.
Bye-bye.